Good morning, Gabby. I'm going to try to shoot a couple very short videos that you can watch on YouTube to help you understand the content you're missing. I talked to your mom. The only thing we really want you to know about for the sound unit is really about the speed of sound and something called the Doppler effect. So I'm going to put together two short videos. I'll try to keep them under 5 minutes or so. This first one's going to be a quick review about sound and ties back to our wave unit we studied. And I will kind of walk you through the equations and how to use them, and then you can try the speed of sound homework that Mr. Deaver put up on Google Classroom. I think the answers are in parentheses, so you can check your work and make sure you get that. We probably won't collect them just to make sure you know how to do these types of problems for the final exam. So anyway, I'm going to get started on a quick unit on sound. I'll do another video in just a few minutes about the Doppler effect. So I think you were here for part of this. Please ignore a couple of these slides. Remember sound, and back in the wave chapter, you talked about two different types of waves, mechanical waves and electromagnetic waves. Sound waves are mechanical, so they need a medium to move through. So sound has to travel through some sort of material, and usually the material for sound, of course, is air. So if there's air in the room and you talk, the sound will travel through that air and come to your ear. If we were to evacuate an area, so for example, out in space, it's empty. So there's a movie back in the 80s when I was a kid called Alien, and the tagline was, "In space, no one can hear you scream," because in space there is no air, there's nothing to carry the sound, so space is silent. So again, sound's a mechanical wave. The other thing we would like to remind you about is sound is longitudinal. So remember back we talked about mechanical waves can either be transverse, they vibrate up and down, or they can be longitudinal. And so if we look at a tuning fork, for example, a tuning fork vibrates back and forth, it will take the air and it will vibrate the air back and forth, so the wave propagates horizontally and the particles move parallel in the same direction. So I think Mr. Deaver talked about this as well. So sound is a different type of wave. It's a longitudinal wave. It's the best example of a longitudinal wave. And I believe, again, Mr. Deaver showed you a little clip like this. So if we look at transverse waves, they shake up and down. A longitudinal wave vibrates back and forth. And what we really mean by that is the particles. So the room is full of air. The air particles don't move across the room. It's not wind. So the air particles vibrate back and forth. So if you sing, oh, please excuse that, but if you sing that frequency of that sound wave vibrates the air back and forth, the wave passes through. So you can see these. The energy passes horizontally to the right, but the particles move back and forth to the right, so they're parallel. So that's what makes it a longitudinal wave. And again, I think you did this earlier. So this is kind of the same way. We have these areas where the air is compressed, we call it compression, and where the air is spread out, we call it rarefaction. And the length, the distance between a compression and a compression is wavelength. It's very similar to what you did with transverse waves. We do a demo out in the hallway where we have the cups with the string. It actually does work, but these, the old phones, the old phones, I don't think I've ever used them this way, but we're just showing you the phone technology has changed. Now the other thing that's kind of important is the speed of sound. Sound has a finite speed, and you've probably witnessed this when you see a thunderstorm. You'll see a flash of light. That light arrives almost immediately. Light travels very, very fast, but sound travels much slower. It still travels pretty quickly, but it travels much slower. And the speed of sound depends on what it's traveling through. So sound travels relatively slowly through gas. Through air, for example, this is about 3 football fields per second. So it's still pretty quick. It's around 700 something miles per hour. As it goes into something more dense, like a liquid, it goes faster. If it goes to a solid, it goes even faster. So sound travels in generally, the more dense the medium or the stuff that it's moving through, the faster the wave goes. Like I said, most of the time we're talking about the speed of sound through air. So these numbers are about 700 miles per hour. And that kind of makes sense. If somebody talks to you, you don't have to wait. You don't see their lips move and wait a couple of seconds for the sound to get there. It gets there pretty quickly. So that's kind of an important thing. Now we have an equation. Well, first of all, we go into the lab and try to find the speed of sound. And one way of doing it, which doesn't work well, is to go down to the football field and have people line up and then make a big noise and time it. The reaction time is is too slow. So you'll never get a good speed of sound measurement by just doing distance over time in that traditional way. So what we do in lab is we actually use an echo technique. And although this sounds really obvious, it's kind of important. When you make a sound, so for example, ships will send down a sound wave down to the bottom of the ocean. That sound takes time to travel down, hits the bottom, comes back up. And we can actually time how long it took to go down and come back up. So the key thing here is that it has to travel a distance down and then the same distance back. So you have to double the distance. Bats use this to find food. They send out sound waves bounce off the food, comes back, and the bat knows where the dinner is. And in lab, we're going to do essentially this. We're going to make a noise, have it hit something, and come back. We're going to time that. So if this were 50 meters away, we'd have to say the sound travels 50 and then another 50 for a total of 100 meters. And if we knew the time for the total trip and knew the distance of the total trip, we can get the speed of sound. So that's the idea. This is old pictures of me in high school. Now, the way we're going to do this is in lab, the way the class did it, is we had a tube that was closed off at one end. So this is essentially our echo chamber. So we're going to make a sound. There's a microphone to catch the activity. We're going to clap our hands or click our fingers. Sound's going to go down the tube, hit, bounce off, and come back out. And the microphone's going to record the sound and its echo. So we'll be able to find the time and the distance for that and calculate the speed. So that's the idea. Now on the computer, it looks like this. The computer can do this because sound's traveling so quickly. We can't do it with a stopwatch. So we're going to make a sound at some point in time. The sound's going to travel down the tube, hit, and come back, and then we'll hear the echo. So sound goes down the tube, it comes back to the echo. So we're seeing, so this time interval is really for the distance down and the distance back. And from that, we calculate the speed of sound. Now, to calculate the speed of sound, we have to make a correction for the fact that sound travels through air at a certain speed based upon its temperature. So this is an equation you'd probably like to write down. It says the velocity of sound equals, and this is for air, just a known value, it's 331 meters per second. And then we make a slight correction for air temperature. If the air is warmer, it goes a little faster. So we say if the air has some temperature, which of course it does, it's 0.6 times the temperature in degrees Celsius. So if the air is 0, it travels 331, but for every degree that's warmer than 0, it will travel 0.6 meters per second faster. So typically we say room temperature is 20 degrees Celsius. That's about 70 degrees Fahrenheit. So we say that would be 331 plus 0.6 times 20. This, of course, will be 12. So the velocity of sound at room temperature is 343 meters per second. And again, that's a little over 3 football fields per second. Now, this is a number we use a lot. So, and this is only at 20 degrees Celsius. But that's typically what we use. So if you're ever doing a problem and it doesn't stipulate what the temperature is, assume it's 20 and the speed of sound will be 343 meters per second. So that's a number you need to know. So we went into the lab and tried to get the speed of sound using the echo technique, and the kids came up with very, very close numbers to 343. And we calculated percent error. It's very, very small. So this equation right here is kind of a key equation you want to write down. When you do the homework set, like I said, Mr. Deaver will give you the temperature, and you'll have to calculate the speed of sound for that temperature, or it will just be 343. So homework number 1, which you can find, it's going to be a bunch of basically manipulating the equation. Remember that it really comes from our equation 2 from kinematics that distance equals VIT plus 1/2 AT squared. But of course, sound is not accelerating, so the A is 0. So this whole term goes out, and we get our familiar equation D equals VIT, or velocity equals distance over time. That's the exact same equation, just rewritten. So on the homework, you're going to use these equations back and forth. Again, remembering that V is 343, unless you have to calculate it for a different speed. Okay, so that should get you started on the first homework. If you have any questions on that, just shoot us back an email. I'm going to make a second video in just a minute about the Doppler effect, and I'll explain that as well. All right? Again, give us a call or shoot us an email if you have any questions.